In our last lecture, I talked about hypothesis testing, and I briefly reviewed what I referred to as the unofficial step 2.5 of hypothesis testing, data cleaning. I provided a brief overview of data cleaning during that lecture. We will now return to look at the concept of data cleaning in more depth before diving into tests of statistical analysis. Upon completing this lecture, students should be able to compare and contrast random versus non-random missing data, discuss remedies for missing data, explain how to identify outliers, discuss remedies for outliers, and describe how normal distributions relate to data cleaning and statistical analysis. Before actually analyzing their data, investigators must ensure the data are free from errors. This process is called data cleaning. Data cleaning may feel like a tedious step in the statistical analysis process, but it is essential that investigators perform data cleaning because if the data are not accurate, the inferred results obtained from inferential statistics will not be accurate either. Errors in data can occur in any study and may be introduced via missing data, outliers, incorrect data entry, or data loss. Violating the assumptions of chosen statistical tests can also result in data error. As investigators, we need to understand how to assess for and manage data errors. As consumers of research and literature, we need to be able to examine the statistical findings for how errors have been identified and treated during data analysis. The quality of the findings relies heavily on how missing data and outliers were handled. This is because errors are a threat to both internal and external validity. So, let's take some time to look at the different types of errors and how to ethically address them. We will begin by discussing missing data. Missing data can occur when a study participant or subject either deliberately or accidentally omits responses to a variable. You may see this in a survey where a participant chose or forgot to answer a question. Missing data can also occur when an investigator has not found a way to measure a variable or did not think ahead to measure a given variable, which can be a really challenging concept, which is why you should really spend a lot of time before conducting your study, reviewing with others, and ensuring that all of the variables of interest are being measured. Sometimes when data is missing, it is simply a problem of transcription. In other words, the person entering the data into the software system mistakenly omitted a value or a set of values. Transcription errors can be very easily corrected by returning to your original raw data and then updating your statistical software to include the missing data. So you should always begin by checking for transcription errors if you identify missing data. If missing data are not the result of a transcription error, then you need to determine, is there any pattern to the missing data? The pattern of missing data has to do with, is the missing data random or non-random? Missing data are considered random when they are scattered within the database, and there is no pattern or relationship. In contrast, non-random missing data have an apparent pattern to them. Non-random missing data are more problematic than random missing data because the pattern can jeopardize the results as well as jeopardize both internal and external validity. So what do I mean about looking for a pattern? You want to look at, was there a specific question that participants refused or chose not to answer consistently? Was there any pattern that maybe data points are missing for participants of a given age or a given gender? Are there any types of consistencies you're noticing about the data that is missing? Once we have determined if there is a pattern to the missing data, the next consideration is how much data is missing. In general, the problems related to missing data get worse as the amount of data that is missing increases. However, there is no simple answer for how much missing data can or should be tolerated. We're now going to discuss how do we respond to missing data. The method you choose to respond to missing data is very important because missing data can impact the generalizability of your results. There are several potential remedies for responding to missing data. The simplest way to deal with missing data is simply to delete the cases with missing data and run the data analysis with only complete cases. In other words, if you have participants that did not answer all of your survey questions, rerun your data and only include the participants who answered all the questions. While this approach is very simple, it should be used with extreme caution and is only appropriate if the missing data are random and the amount of missing data is small. If there is a large amount of missing data, deleting cases with missing data could seriously distort your results. Similarly, if there is a pattern to the missing data, deleting missing data could significantly impact the outcome results. This begs the question of how much data is okay to delete. Just like there is not a hard and fast rule of how much missing data is acceptable, there's really no hard rule of how much missing data is okay to delete. However, the general consensus is that if 5% or less of your data is missing and the missing data is random, it is okay to proceed with deleting the missing data cases. Another approach to responding to missing data is to estimate the data values for the missing data and use the estimates in your analysis. Estimating the missing data points can introduce bias into your sample, but it is a useful alternative to deletion when the sample is small. While there are many methods that can be used to estimate missing data, we will discuss the two most common: using prior knowledge or substituting with means. Using prior knowledge is generally the simplest estimation approach. In this approach, investigators make a well-educated guess about the missing data based on prior knowledge of their study focus. This method does rely on the investigators having extensive background knowledge on the subject and the population. The other option would be to use previously obtained sample means in replacement of your missing data. This method, while more time-consuming than using prior knowledge, tends to yield more accurate results because it is based on previous data collection. However, this approach is also not without limits, as it will reduce the variability of your data set, and it is highly unlikely that the previous data that you collected and are replacing the missing data with would be the exact same values as the data that you are missing. The next error that we are going to discuss is outliers. Any data value that is unexpected or outside the expected range of values for that variable is considered an outlier. Outliers introduce error into the analysis, so it is very important that we identify as well as handle them appropriately. Determining if a data value is an outlier can be a subjective process and may require multiple techniques to get the clearest answer. The easiest and quickest way to identify outliers is to look at the visual representation of the data. If you think back to our lecture on displaying data visually, you should recall that many different types of graphs can help us identify outliers. The scatter plot is most commonly used to identify outliers. However, histograms and box plots can also be helpful. And I have a picture of these on the slide. In the histogram, the outlier value will appear either far to the right or far to the left from the other data values. And you can see that in the first picture. In a box plot, the outlier will be marked above the upper whisker or below the lower whisker and is usually denoted with an X or a circle as shown in the middle picture. In a scatter plot, outliers are either far to the right, to the left, above, or below all the other data points, as can be seen again in the picture. Depending on how far from the rest of the data the outlier falls, visual representation may not always be a clear indicator to help you identify outliers. The outliers in the pictures I provided are all very easy to see, but these are very extreme outliers. The other method you can use to identify outliers is to examine the z-scores of the raw data. We briefly discussed this process of z-scores in our lecture on comparing sample data to the population in Module 2. To compute the z-scores for the raw data, you will want to use computer software to minimize the error that might occur from computing this by hand. You will then need to assess for unusually large or small z-scores. A general rule to use is that if the z-score for a data set is outside of the range from -3 to +3, then the data point is an outlier because we would expect 99.8% of all data values to fall between a z-score of -3 to +3. Outliers can be a very serious problem in data analysis, and like missing data, they can threaten both the internal and external validity. Outliers are a problem because by their very nature, they skew your results. You should recall from previous lectures that skewing means that the outlier is pulling the mean or the average in one direction or the other. Researchers care about this because a data set that is skewed means the assumption of normality is violated. In other words, when a data set is skewed, the data are not normally distributed. As we will discuss briefly on the upcoming slides and in more detail in future lectures, certain tests of statistical analysis, which are called parametric tests, require that our data be normally distributed. Anytime you have data points that are outliers, the first thing you should do is check for a transcription error. Remember, you and those you work with are humans, so there is always a chance that data was entered wrong. Check that first. If you confirm that an outlier is not the result of a transcription error, the next thing you want to consider is if the outlying data value is part of the intended population for the study. What do I mean by this? For example, if you defined your population as nurses over the age of 65 and you find an outlier of a nurse who participated in your study but was 37 years old, you are going to want to delete the data you collected on this nurse because they are not part of your intended population. And even though you explain the participation requirements, sometimes this does happen. This is the only time you should delete outliers. You should not delete outliers from your data for any reason other than the fact that they are not part of your intended population of study. Our textbook suggests that you can respond to outliers by arithmetically manipulating or transforming the data or changing the scores of the outliers. From a personal perspective, I am not supportive of either of these methods. In my humble opinion, it is through actions such as transforming the data or changing the scores that statistics gets the reputation of making the data say anything you want, and you may have heard that before. the methods used to transform data or change the scores are beyond the scope of this course. I would argue that the more ethical approach, instead of transforming data or changing scores, is to accept that your data are not normally distributed, accept the fact that the outlier is skewing your data, and proceed by analyzing your data using what is called a non-parametric test of statistical analysis, because non-parametric tests do not require your data to be normally distributed. We began this lecture by discussing the importance of data cleaning to ensure that our results of statistical analysis would be accurate. Data cleaning also helps us to determine what the appropriate type of test of statistical analysis should be. If you remember, in our lecture on hypothesis testing, step 2 was choosing an appropriate statistical test. And step 3 is ensuring that we chose the right test and we met the assumptions. All tests of statistical analysis have assumptions that must be met in order for the analysis to be considered valid. We will look at this more in our upcoming lectures, but what you need to understand right now is that normal distribution is an assumption for parametric tests, but not for non-parametric tests. In general, in step 2 of hypothesis testing, you are going to choose a parametric test because these tests are generally more powerful than non-parametric tests when the data is normally distributed. And we generally go into a project assuming that our data will be normally distributed, but then we must assess for normal distribution. If the data is not normally distributed, parametric tests may not provide valid results because we are not meeting the assumption of normality. Thus, we would use a non-parametric test, which does not have normal distribution as one of their assumptions. When the data is not normally distributed, non-parametric tests are the best option for getting valid results. So, to wrap up our discussion of data cleaning, which was a focus on my step 2.5 of hypothesis testing, data cleaning is an important first step for data analysis. Errors should be corrected before analysis is conducted to ensure the most accurate results possible. Errors can include missing data or outliers, both of which must be handled carefully so to not jeopardize internal or external validity. If missing data or outliers are identified, always begin by checking for transcription errors. If transcription errors are not present, move on to the other methods we discussed for responding to errors. Do not delete outliers unless the data value is an outlier because it is not part of the intended population study. After cleaning your data, if the data is not normally distributed, you may need to proceed with analysis using a non-parametric test, which would lead us into step 3 of hypothesis testing. And we will shortly head into some lectures on the specific parametric and non-parametric tests that I have been referring to over these past couple of lectures.